So this is a topic related to mechanical properties of solid. Okay, this is otherwise called as strength of material or mechanics of material. So the study related to stress and strain. Okay, or it is otherwise called as strength of material. Okay, so this subject is very important, and we taught it extensively in mechanical engineering or civil engineering when we design different structure, when we design machines, like even if you design aircraft, design an engine or design a bridge or any structure. Okay, so everywhere this is very important. Okay, so your structures can be made of steel, it can be made of like different material, made of aluminum or made of composite, all these things. Okay, so any structure, when you design a structure, the structure will be subjected to a load, and under loading how the structure is behaving. Okay, so the structure will have a certain strength, like steel will have higher strength than aluminum will have higher strength than wood. Okay, so the amount of load that you can put on steel, same amount of load you cannot put on aluminum. Okay, it will fail. Okay, so I have taught you the stress strain curve. For example, for steel, the yield strength. Okay, that yield strength is around 500 MPa. For steel it is 550 or so MPa, whereas for aluminum it is around 450 or something like that. Okay, so steel is stronger than aluminum, and so different material will have different strength. So we measure it mostly for ductile material as either as yield strength or ultimate strength and all that. Okay, so so this is a very important topics. So this is um, for designing any machine or for designing any structure. The knowledge of mechanical properties of fluid or strength of material is very important. Okay, so here I'll just give you some brief introduction on what are the different things we should know here. Okay, and then we will do some numerical. Okay, so quickly, so stress, what is strain and all. Okay, so stress, sigma, we write it as force per unit area. Okay, so if this is my rod. Okay, so I am applying some force. My cross section area is say A. Okay, and if it get extended by some length, say delta L. Okay, so let us say this get extended by some length delta L. Okay, so this is L, delta L, and if the original length is L, okay, so this is L. Okay, if this is the case, your stress is equal to F by L, and there is something called your strain. Okay, your strain, which is written as epsilon, which is equal to delta L by L. Okay, so this is then there is something called Young's modulus, Y. Okay, which is Young's modulus, which is equal to your stress by strain. Okay, so this is Young's modulus, and then there is something called your shear stress and strain. Okay, so let me say, like when you apply the load applied is parallel to the surface, then that is called shear stress and shear strain. So let us say this structure is fixed at, it is grounded like this, and you are applying a force F here. Okay, and it is, this load is being applied. This is a 2D diagram, so if you see it in the isometric view, it is getting applied on some area. Let us say some area on some area A it is being applied. Okay, so some area A, if it is being applied on some area A, so let us say this is A. Okay, so the load is being applied parallel to the surface. But here if you say the load is, so if this is a rod of diameter, the load is applied perpendicular to the surface, whereas here the load is getting applied parallel to the surface. Okay, so something like this. So the load is getting applied parallel to the surface, right?
Yeah.
So this is my load. Okay. So here there are three things. One is Young's modulus, one is modulus of rigidity, another is your bulk modulus. Okay. So this modulus of rigidity, here the stress will be like say these are all longitudinal. Okay, longitudinal stress, right? That is. Okay. Then we will have some shear stress, shear strain, and all that. Okay. So this shear stress here we write it as shear stress. Okay. Shear stress tau is equal to force by area. Okay. Here you can see the force is applied parallel to the surface. Okay. And shear strain. Okay. Shear strain. So that shear strain, what it is actually, so if you see, originally it is here, but after deformation it will get deformed by an angle, let us say, it gets deformed by an angle theta. Okay. So this will get deformed. Okay. So some parallel line if you draw, so this is my angle theta. Okay. So this angle theta, and let us say it is getting deformed, so this distance, if you see this distance, okay. So let us say this length is L, okay, original length is L, and let us say this length is delta L here.
Yeah.
Or you can write it as delta X to avoid confusion. So shear strain is equal to delta X by L, which is equal to theta. Because it is del X and del L, so strain is unitless. Stress is unit is
Newton per meter.
Newton, this is Newton, and this is meter square. Okay, so and strain is unitless. And then there is this Young's modulus, then this is called shear modulus or rigidity modulus. Shear modulus or rigidity modulus, or we call it as, which we read as G. Okay, is equal to this tau by
theta.
Theta. Okay, so that is the shear strain, you can say, tau by theta. Okay. So this is about shear strain. Okay. Then there is something called
bulk modulus.
Bulk modulus. Okay. Bulk modulus. Okay. So here you can see this. You can put the picture like this. So you have, let us say you have some volume. Okay. So you are applying some pressure. Okay. So you are applying pressure. So you are applying pressure, and after applying pressure, this has the compressed condition is this. Let us say it is compressible liquid or whatever, right?
Yeah.
When you okay, so you are applying a pressure, and before compression it is like this, after compression it is like this. So this pressure you are applying is P, okay?
Yeah.
And before compression the volume was V, okay? And after compression the volume is V minus delta V, okay? So here bulk modulus we write it as K, okay? Bulk modulus we write it as K, bulk modulus. Okay. K is equal to pressure divided by del V by V. Okay. This is called as volumetric strain.
Yeah.
Volumetric strain. Okay. So this delta V by V is called volumetric strain. Volumetric strain. Okay.
Yeah.
So here also, and there is one relationship between this E and G. Okay, so G, just remember this. I have seen some JEE questions. It has come like G is equal to E divided by 2 into 1 plus V. Just remember. Okay, So what is this nu? This nu is the Poisson's ratio. Okay. So when I'll just give you what is the meaning of that Poisson's ratio. So nu, which is Poisson's ratio. Poisson's ratio. Okay. So what happens like when you are stretching, suppose when you are stretching a rod, so because it will get stretched, so it will get compressed in the lateral direction. In longitudinal direction it will get stretched, and in the lateral direction it is a magnified view. Okay.
Yeah.
In lateral direction it will shrink. Okay. So when it shrinks, let us say the original diameter is d, okay, and then the final diameter is say d minus delta t, okay, and the original length is L, okay, the original length is L, and the final length is L plus delta L, okay. So the Poisson's ratio is nothing but which is equal to del lateral strain by longitudinal strain. Okay, so what is lateral strain? So that is del d by d. Okay, that is lateral, in lateral direction, and
by longitudinal.
by longitudinal strain del L by L. Okay, so and it is always a negative, because if length increases in del d by d, it will be negative. This is positive means this is negative. Okay. So this is called Poisson's ratio, which is nothing but lateral strain divided by longitudinal strain. So this is nothing but lateral strain by
Longitudinal strain.
longitudinal strain. So this is Poisson's ratio. So there is this Poisson's ratio for steel. So mu Poisson's ratio for steel is something around 0.3 or whatever. Okay. So this rigidity modulus is related to Young's modulus by this. So rigidity modulus is always less than Young's modulus. Okay. So this if you put here 0.3, it will be 1.3. So 1.3 into 2. So E divided by 2.6. So this I have seen in JEE. There are some questions. What is the relationship between rigidity and Young's modulus? Just remember, G is equal to E divided by 2 into 1 plus nu. Okay, this much you have to remember. Okay, you don't have to derive. It is a long derivation, no need to derive. Okay, so now you understood what is longitudinal strain, what is shear strain, what is bulk modulus. Okay, so with these formulas you can solve many questions. Okay, you take a picture. So now you understood this. Okay. Okay. So you understood what is Poisson's ratio. Here you can see this relationship. Okay, so so with this we will try to solve some numericals. Okay. So and you took a picture.
Yeah.
Okay, so there is something called the strain energy. Okay, the elastic potential energy stored. Okay, so when you have a wire, okay, so let us say I have a wire. Okay, let us say it's a thin wire. Okay, so if I put a load on this, okay, if I put a load on this, it is like if you imagine it is like a spring, or we were doing that spring, it is kx into x.
Yeah.
So half kx square. Okay, that one we had potential energy. In simple harmonic motion we have done it. So just for a wire, you just remember strain energy stored. Strain energy stored in a wire is equal to wire per unit volume. Okay, per unit volume. Okay?
Yeah.
That will be equal to half into stress into strain. This much you remember. Okay, so this wire, let us say this wire is of length L. Okay, so this wire is of length L. So let us say you are putting some weight. So that weight, is nothing but the force applied.
Yeah.
And this wire will have cross-sectional area say A. So you know force is equal to your weight, and you know cross-sectional area of the wire is equal to pi by 4 d square. So knowing all this, you can find out, if you know the Young's modulus of the wire, you can find out what is your strain and all.
Yeah.
So, or they will give the strain. Okay, if they will say that okay, this much of force is applied and the elongation is this much. So elongation by original length is your strain.
Yeah.
Force is the whatever weight is being applied. So let me say I am applying 10 kg weight there. Okay. So 10 kg, that means mg. Okay. So 10 into 10 decimeter per second square. So 100 Newton I am applying. Okay. So 10 kg into 10. So 100 Newton, that is my force.
Yeah.
Okay. Then area of cross section of this wire is pi by 4 square. They will give the diameter of the wire in mm or whatever. So normally we do it in MPa, Newton per mm square. So we don't, in this
Very small
procession normally
deformation.
it is mm, so we do it. So just remember 1 Newton per meter square, 1 Newton per mm square is nothing but 1 MPa. Okay. So 1 MPa is equal to 10 to the power 6 Pascal. Okay. So this is, we convert, I have explained you this. Okay. So just remember strain energy is equal to half stress into strain. So if you want to, that is for unit volume.
Okay.
So if you want per volume, then you have to the length into the cross sectional area, that is the volume.
Yeah.
You can multiply that.
Yeah.
But normally this formula is important. Okay, half stress into strain. That is the strain energy stored per unit volume. And then there is another important thing is your stress strain curve. Okay. So normally for mild steel or some material, for aluminum it is different. So in the y-axis you will always have stress. In the x-axis you have strain. Okay, so normally you will have, I have explained, so you will have a scale, measuring scale. When you are putting something weight, higher weight, for every weight, say weight W1, this is delta L you will measure. Weight W2, this is delta L1 you will measure, delta L2 you will measure. Then accordingly you will draw the stress strain curve. So this weight is nothing but your F1. So normally I am putting stress means this is stress is nothing but your force by area. So this area is constant actually. Similarly your strain is delta L by L. So this length is constant. So what I am measuring the change in length, and I am measuring the force like F1, F2 and all. Then divide by area. So in the y-axis you have stress, in the x-axis you have strain. Okay, so this stress strain diagram, it looks like this. For mild steel, it looks like this. So there is some yield point, and then it will go like this. Okay, then it can go like this. Okay. So this is called yield point. Okay, so this is yield. So in mild steel you have a upper yield and you have a lower yield. Lower yield point. So this stress is called sigma y. Okay. So I can draw this. I can draw a line up to this point.
Yeah.
So this is my yield. Okay. This is my yield. Okay. And then this is this. If I draw it here, so a y-axis up to this. If I draw, so this is my ultimate tensile strength, UTS.
Yeah.
That is the maximum stress. Okay.
Yeah.
And here it breaks. So this is
Breaking
my
point.
breaking point, breaking stress or breaking stress. And this is ultimate tensile, the maximum stress that it can take. But there can be, I have seen there are questions like, so before yield point there will be another point. So this is A, let us say this is B, then this lower yield is C, this point is D, and this point is E. Okay, so here A is called proportional limit.
Till this point there is no deformation.
Proportional limit. There is deformation,
But it is proportional.
But it's linear.
Linear.
So stress is proportional to strain.
Strain.
So the slope of this stress strain diagram is nothing but your Young's modulus.
Yeah.
Okay.
Yes.
Let us say OA. Okay. So this OA area is till proportional limit.
Yeah.
Proportional limit. This OA area is till proportional limit, and OB, till OB, that means till yield. Okay. And then C is lower yield, then D is your ultimate tensile strength, and then E is your breaking. Okay. So, and another thing is, there are questions like up to A, the stress strain curves are linear. Okay. And up to yield point, like if you remove the load, the material will come back to its original
There is no
position.
permanent deformation.
So after yield there will be permanent deformation. Before yield, at yield point, if you remove the load, it will come back to your original position. That means it will follow this path. Like loading path is this, unloading path is this. It will come back, so there won't be any permanent strain.
Yeah.
Okay, but beyond it is called the plastic region. Okay, so you can say up to this is your elastic region. Okay, and beyond this region is called plastic region.
Yeah.
Okay, so this region is called your elastic region. Elastic means if you remove the load, it will come back. But once it enters the plastic region, it will not come back to its original position. Okay. So, so there will be some permanent settle. So what happens in the plastic region? If you unload it, it will come back like this. Come back in a line parallel to this line.
Yeah.
Okay, so this much will be your permanent strain that will remain.
Yeah.
Okay. So normally in structures we don't go beyond yield, so we never enter into plastic. Okay, but for some high stress component like gas turbine engines and all, when temperature is very high and it is rotating at some 10,000, 12,000 RPM, very high centrifugal force and all, so that time it may get into plasticity.
Go beyond it.
Beyond it. But normally for ground-based structure and for normally we don't allow it to go beyond it, because you don't want the structure to have a permanent set. Okay, it should operate under within elastic. Okay.
Yes.
So so that is about the stress strain diagram. Okay. So with this, this is the summary of the mechanics of solid that you have till this point. Okay. So next session we will do some numericals on mechanics of solid.
We will take picture.